Welcome back, everyone, to the Foundry by Forge College. I am incredibly excited to be hanging out with you today. In our previous explainer, we laid down the foundational concrete for cryptographic hashes. We learned they rely on two absolute non-negotiables: deterministic mapping, which basically means the same input always gives you the exact same output, and fixed-length digests. So, whether you feed it a tiny two-letter word or literally the entire encyclopedia of human history, the output is exactly the same size. Today, we're taking those basics and looking at how they actually protect our data from some very determined, very clever digital thieves. Okay, let's dive into this blueprint for today's explainer. We'll be hitting 1. The cryptographic puzzle box. 2. 3 rules of resistance. 3. Attackers and real-world defenses. 4. Triggering the avalanche effect. And finally, 5. Calculating the work factor. And hey, if you're a beginner, don't sweat it at all. We have a very clear, logical path through the math today. All right, kicking things off with Section 1, the cryptographic puzzle box. Time for some concrete mental models. So let's step away from the abstract algorithms for a second and build a really physical mental model here. But first, just a super quick reminder, a cryptographic hash function takes any input you give it and spits out a deterministic, fixed-size output. These two functional prerequisites, they're the absolute bedrock. I mean, every single security assumption and bit of math we're about to discuss is only possible because of determinism and fixed-length outputs. Think of a cryptographic hash function as a magically sealed puzzle box. You can put literally anything you want inside this box, but once it's closed, no way. You absolutely cannot look inside. The exact moment it seals, the box deterministically stamps out a short, fixed-size warranty tag on the outside. That tag right there, that's your digest. And because of determinism, if you put the exact same items in a second box, it will absolutely stamp out the exact same warranty tag. Moving right along to Section 2, 3 rules of resistance. We call these the big 3. Okay, so we've got our sealed box and our stamped tag. Now, to actually protect our data, this whole system needs 3 specific mathematical properties, affectionately known as the big 3. We've got pre-image resistance, second pre-image resistance, and collision resistance. And what's cool is each one of these is designed to completely shut down a radically different type of hypothetical cyber heist. Now, what's really interesting about this is just how differently these attacks work. Pre-image resistance means the attacker only has that warranty tag, the digest. Their goal? To magically reverse engineer the contents of the box. I mean, with modern 256-bit hashes, this is hilariously futile. Then you have second pre-image resistance. Here, the attacker already has a filled box and its tag, say a perfectly legitimate file. Their goal is to find a completely different file that magically stamps out the exact same tag. Again, mathematically infeasible. And then there's the third heist, collision resistance. In this scenario, the attacker hasn't been given a specific tag to target, and they don't have a starting box. They have total, absolute freedom. They just want any 2 different boxes that accidentally stamp out the exact same warranty tag before any commitments are made. It's a massive search problem, for sure, but because they have total freedom to pick both inputs, it is slightly easier for the attacker than the other 2 methods. Which brings us to Section 3, attackers and real-world defenses. Let's look at some real attacker models. And this brilliantly illustrates how these attacker models operate out there in the wild. Say you're verifying a firmware update. The attacker is trying to swap the legitimate file for a malicious one without changing the hash, right? That requires second pre-image resistance. But if you're dealing with, say, an unsalted password database leak, the attacker already has the digest and just wants the original password back. That's a straight-up pre-image attack. So checking a firmware update requires totally different mathematical guarantees than storing a user's password. But relying on just a hash function alone? Not going to cut it. We need defense in depth. Even perfect hash functions absolutely need backup layers, things like cryptographic salts, nonces, and versioned algorithm identifiers. Why? Because nation-state adversaries with vast resources are basically always looking for algorithmic shortcuts. In our various learning tracks at Forge College, we constantly emphasize this. Real security means ensuring that breaking a system requires an attacker to defeat multiple mechanisms, not just exploit one tiny mathematical weakness. All right, Section 4, triggering the avalanche effect. Prepare for some global chaos. Let's move on and see how this builds, right? How do hashes act as the ultimate anti-tampering mixing machine? Well, imagine the inside of our puzzle box is full of these intricate interlocking gears. The avalanche effect dictates that if you alter just a single tooth on one tiny gear in the input, the resulting warranty tag doesn't just change a little bit, no. It causes unpredictable, massive bit flips across the entire output digest. A micromutation in the input causes global high-entropy chaos in the output tag. It's wild. And this avalanche effect, it's absolutely crucial for tamper detection. Think about it. If small input changes only made small output changes, attackers could easily just play a game of hot or cold. They'd tweak their malicious file bit by bit, watching the digest get closer and closer to their target until, boom, they break the system. The avalanche effect completely destroys their ability to play hot or cold. All right, final stretch. Section 5, calculating the work factor. Let's talk about attacker effort. Now that we know how the algorithm scrambles an attacker's efforts, let's do a little bit of fun attacker math to see exactly how safe your data is. When we assess effort, we compare naive brute force inversion, which is finding a specific target for a pre-image attack, versus something called the birthday attack. The birthday attack is used for finding collisions, where the attacker doesn't care what the target is at all. They just need any two inputs that produce the same output. So the crucial point is this huge number right here. 2 to the power of n, where n is the number of bits in your digest. For a pre-image or second pre-image attack, the work factor is roughly 2 to the n evaluations. If you're using a modern 256-bit hash, 2 to the power of 256 is a number so staggeringly huge that an attacker using naive brute force will literally be guessing until the sun burns out. But watch what happens with collisions, because the attacker can freely search both sides of the equation using the birthday paradox. The math drops drastically. The work factor becomes 2 to the power of n divided by 2. That literally halves the exponent. Suddenly, a 128-bit digest isn't 2 to the 128th power of work, it's just 2 to the 64th power. And 2 to the 64th power is a number that modern specialized hardware might actually be able to reach in a reasonable time frame. Which brings us to the ultimate question for your own systems. Is your chosen digest length strong enough to survive tomorrow's computing power? You always have to map your specific use cases to the required property. Translate that to a work factor target, and ensure you have enough bits to outlast the adversary's budget. It's just a fascinating game of mathematical chess. Hey, if you want to dive deeper into this subject and learn how these properties secure vast Web3 systems, I highly encourage you to visit forge.college. There is a whole world of blockchain fundamentals waiting for you there. Thank you so much for joining me on this explainer today, and keep wondering, as computers get exponentially faster, what will the cryptography of tomorrow need to look like to keep our puzzle boxes sealed?